Good morning, dear students. Welcome you all to the module 4. In this module, we are going to discuss about osmotic pressure. So, before going to the osmotic pressure, what is osmotic pressure, how it is useful for the calculation of molar mass, etc., we should understand the definitions of diffusion and osmosis. So, what is diffusion? So, diffusion is a process where the movement of solute molecules from more concentrated solution to the less concentrated solution, and that of the solvent molecules from low concentration solution to the high concentration solution. So until it gets a uniform concentration. So this is for example addition of water to the copper sulfate solution. So the copper sulfate molecules will move from copper sulfate to the water, and water molecules will move from water to the copper sulfate solution, so that will get uniform solution. So but what is osmosis? So the osmosis means the movement of pure solvent molecules from solution of low concentration to the high concentrated solution, so through a semi permeable membrane, is called as osmosis. Here the movement of solute molecules is stopped because the semi permeable membrane, it can allow only one type of molecules through it, so the remaining type of molecules it is not allowed. That's why through semi permeable membrane the movement of solvent from low concentration to high concentration is called as osmosis. And this process was observed by Abbe-Nollet in 1748, and he called this phenomenon as osmosis. And this osmosis we can clearly observe with the behavior of egg in water and corn soup. So if you add egg to the water, and here the egg membrane, the cell membrane, egg cell membrane acts as a semi-permeable membrane, and here we can observe the movement of water from the solvent to the egg cell, so that the swelling of the egg will observe. If the same egg, if we dip in the corn soup or salt solution, then the water from the egg cell will start moving from the cell to the corn soup, so that the shrinking of the egg is observed. So this is the osmosis process. This egg swelling in the case of water, egg shrinking in the case of corn soup, it is due to the process of osmosis. Now coming to the different types of semi-permeable membranes, as we already seen in the case of eggshell behavior, the egg membrane, cell membrane acts as a semi-permeable membrane. So means the plant cell membranes and animal cell membranes like pig's bladder also acts as a semi-permeable membrane, and most of the common laboratory membranes are copper ferrocyanide, so which is very strong and which can withstand very high pressures. So this one we can synthesized in the laboratory by undergoing the electrolysis process between potassium ferrocyanide and copper sulfate. And now we can observe the various definitions of osmotic pressure. So osmotic pressure is defined as the excess pressure which must be applied to a solution in order to prevent the flow of solvent into the solution through the semi-permeable membrane. Means the excess pressure must be applied to the solution, so to stop the movement of solvent from one phase to the one concentrated solution to the other concentrated solution, so through the semi-permeable membrane. Or we can also define in terms of vapor pressure of the solution and also solvent. So osmotic pressure is the excess pressure which must be applied to the given solution in order to increase its vapor pressure until it becomes equal to that of a solvent. Or it is also defined as the negative pressure which must be applied to the pure solvent in order to decrease its vapor pressure until it becomes equal to that of solution. Or the osmotic pressure is the hydrostatic pressure produced when a solution is separated from the solvent by a semi-permeable membrane. And this definition we can clearly understand by using this thistle funnel experiment. So we'll take a salt solution in the thistle funnel or any colored solution in the thistle funnel tube, and this bottom of this thistle funnel is attached to the semi-permeable membrane, and which is dipped into the a container which is having the solvent, that is water. After some time, the water molecules or solvent will start moving from the container to the thistle funnel tube through the semi-permeable membrane to get the uniform solution. So, and in the same way, we'll observe some rise in the liquid or solution in the thistle funnel. So, this liquid rise in the funnel after some time is multiplied by density of the solution will give rise to the osmotic pressure. So with this, a few knowledge regarding the osmosis and osmotic pressure, we'll move on to the calculation of molar mass of non-volatile solute using osmotic pressure. So before going to that derivation of the equation of osmotic pressure and molar mass of the non-volatile solute, we should understand the behavior of dilute solutions. So, the scientist, namely Van 't Hoff, he has observed various dilute solutions and he has given his conclusion like this. A substance in dilute solution behaves exactly like a gas, and the osmotic pressure of a dilute solution is equals to the pressure exerted by a gas. Means solute in dilute solution, it just behaves as gas, and the osmotic pressure is equals to the pressure exerted by that gas. Hence, we can apply all the gas laws to the dilute solution, so that we'll get the combined equation for the dilute solution. Like ideal gas equation, we'll get some equation for the dilute solutions. So first we'll see the laws of osmotic pressure. The first one is Van 't Hoff's Boyle's law for dilute solutions. And this law is mainly tells about effect of concentration on the osmotic pressure. So at constant temperature, so this law is at constant temperature, the osmotic pressure of a dilute solution is directly proportional to its concentration or inversely proportional to the volume of the solution, that is dilution, containing 1 mole of the solute. So means osmotic pressure pi is directly proportional to the concentration of the solution or inversely proportional to volume of the solution which contains 1 mole of the solute. Or you can also write these two equations as it is: pi upon C is equals to constant, or pi into volume of the solution also equals to constant at constant temperature, where pi is the osmotic pressure of the solution and V is the volume of the solution in liters, which contains 1 mole of the solute. Now coming to the Van 't Hoff's Charles law. So this law is mainly tells about effect of temperature on osmotic pressure. So if the concentration of dilute solution is kept constant, then the osmotic pressure is directly proportional to the temperature. That is in absolute scales. Osmotic pressure is directly proportional to temperature, or osmotic pressure upon temperature is equals to constant for a given concentration. And 1/2 Avogadro's law. So equimolar solutions of different solutes exerts equal osmotic pressure under identical conditions of temperature. So means equimolar concentrations of solutions, equimolar solutions of different solutes. So different solutes with the equal molarity, so they exert equal osmotic pressure under identical conditions of temperature. Or we can also define the Avogadro's law: the equal volumes of all solutions having the same osmotic pressure and temperature contain the same number of solute molecules. Then we'll get the general equation for the osmotic pressure by combining these dilute solution laws. So according to Van 't Hoff's Boyle's law, so we know that osmotic pressure is inversely proportional to volume of the solution at constant temperature. And according to Van 't Hoff Charles law, osmotic pressure is directly proportional to the temperature for a given concentration. So combining the both laws will get the equation like this: pi is directly proportional to T upon V, or pi V is equals to St, where S is the proportionality constant, also called as solution constant, and which is just similar to the gas equation, that is PV equals to RT. So for n moles of solute in V liters of the solution, the equation becomes pi V equals to NST, or pi equals to N by V into ST. So n number of moles, where N is number of moles of solute in particular solvent. So number of moles upon volume is nothing but concentration, that is molarity. Then the osmotic pressure pi is equals to C into ST, CST. So the above equation is called as Van 't Hoff equation, where C is the concentration of the solution in moles per liter. So this Van 't Hoff equation has some limitations. It is mainly valid only for the dilute solutions which contains non-electrolytes up to 0.1 molar concentration. The percentage of deviation increases with the increase of concentration of the solution. In case of electrolytes, usually we'll observe some higher values than the calculated according to the formula. Similar to ideal gas, this law is valid for dilute solutions at not lower temperature, at not very low temperatures. So it will apply to the moderate temperatures. So now we are going to prove this osmotic pressure is a colligative property, followed by the molecular weight of non-volatile solute calculation by using osmotic pressure. So pi V equals to NST and pi equals to N by V into ST, that is equals to CST, where C is the molar concentration. So then osmotic pressure mainly depend upon number of moles per unit volume and independent on the nature of the solvent. Hence osmotic pressure also is a colligative property. So now coming to the derivation of equation for the molar mass of solute by using osmotic pressure. So then from osmotic pressure equation, that is pi V equals to NST. So if W grams of solute of molecular mass MWT is dissolved in V liters of the solution, then number of moles of solute is equals to W1 by M1. That is number of moles of solute equals to W1 by M1, or if you substitute number of moles in the Van 't Hoff equation, so then pi V equals to W1 upon M1 into ST. So and we can rearrange this equation in terms of molar mass of the solute, that is M1 equals to W1 into ST by pi V. So where M1 is the molar mass of the solute and W1 is the weight of the solute in grams dissolved in V liters of the solution, and T is the temperature in Kelvin scale, and pi is the pressure, osmotic pressure, and S is the solution constant. The values of S in different units are like this. In the same way gas constant for the gas law. 0.82 1 liters atmosphere per mole per Kelvin, or 8.316 joules per mole per Kelvin, or 1.987 calories per mole per Kelvin. So now coming to the relation between lowering of vapor pressure and osmotic pressure. So this is the general osmotic pressure equation for a solute with W1 grams is dissolved in some volume. Then pi V equals to W1 by M1 into ST, or pi V upon ST equals to W1 by M1. And we already know that according to Raoult's law, the relative lowering of vapor pressure for dilute solutions is this one. And in this equation, this W1 upon M1 of solute is replaced by pi V upon ST. Then the equation becomes P naught minus P upon P naught equals to pi V by ST into M2 by W2. That is solvent molecular weight upon a weight of the solvent. Thank you. Thank you once again.